Okay, we're going to try and do cross product with this little screencast. We'll see how this goes because someone apparently shared their little microbes with me on the airplane. And I can assure you that a stuffy head at 2,000 meters is not a happy time. But let's go. So we're going to start with two vectors, A and B. And we want to do multiplication that leads to a vector. And we already did this with magnitude and direction in the right-hand rule, but I'm going to show you how to do it with components now. Okay, we'll start with two full vectors written out in components, A and B. And to take the cross product, we form a matrix and then take the determinant. The matrix has a very specific form. Across the top row, I, J, and K. The middle row is the first vector, in this case A, and the third row, or the last row, is the second vector B. So we're going to take the determinant. So this is really a sort of a mnemonic or a game for doing this. It's a certain set of rules that you follow, the definition of the determinant. So we start by looking at I, and we think about crossing out the row and the column that contain the I. And then we do a cross multiply. AY times BZ minus AZ times BY. That's our first term. Second term, we look at the J, and notice there's a minus sign here, minus J. And then it's the same pattern. Left to right, AX BZ, AZ BX minus. And then finally, last one, Z. A little messy now. AX BY minus AY BX. So there's this pattern. You just follow the pattern. And that's the definition of the determinant. And we use that for determining the cross product. So as long as you know the vectors in component form, you can always do this. And remember, it's right to left minus left to right. And there's this extra sign in here that you have to remember, this minus sign for the J. Okay, let's do some examples. Let's do a conversion problem. So the Mount Ararat station that is just above us is at 3,250 meters. So how tall is that, or how high is that in feet? Okay, well, we need a conversion, and there are a few ways you can do it. The easiest way to do it is to find this conversion right here, feet to meters. So we can just write the original units, 3,250 meters, times a ratio we've constructed, 1 foot over 0.3048 meters. Notice the meters cancel out, and we're left with feet. So if you were punching that into your calculator, it would be 3,250 times 1 over 0.3048. In general, on tests at least, I would accept this expression right here written out as the answer because it is a complete mathematical expression, and you can go on and work the next problem. Okay, let's go to another example. Okay, simple vector sum example. A woman drives 50 miles north and then 10 miles east and finally 25 miles south. What's her final position, magnitude, and direction? So if you made a sketch of this, which I would like to do, we'd start out at some point. We go north, and then we go east, and then we go south, and the resultant vector is the blue one, R. So the easiest way to do this is probably to write the three vectors in components, and I have effectively constructed a coordinate system here, where that's the origin, and the north is up and the east's to the right. So I can write the first vector, R1, as just 50j because of the direction in my picture. The second vector, R2, is just 10I to the right in the I direction. And then this one, which is obviously not to scale, minus 25j. So now I just have to add the components, and remember I had like components. So it's 50j plus 10I minus 25j. So when I add the j's, I get 50 minus 25, that one, and 10I. Alright, so that's the resulting vector in component form, but you were asked for this in magnitude and direction. So we can always find the magnitude and direction. The magnitude is given by the sum of the square roots, the square root of the sum of the squares of the resultant vector here, 10 squared plus 25 squared. And the angle goes as the j component over the I component. So the tangent of the angle, which in this picture is that angle right there, theta, goes as 25 over 10. We could calculate that as the inverse tangent of 25 over 10. And if you look at the picture, right, we implied that that's north, that's east. So that must be north of east. Okay. Nice problem. Okay, let's do a different problem. Okay, let's do this problem where we essentially do everything we know about vectors at this point. So we're going to take two vectors, A and B. We're going to add them, subtract them, find the magnitude, find the angle that A makes with the horizontal axis, find the dot product, the angle between the vectors, and the cross product. Alright, so our two vectors, let's try that again. And I chose vectors that just had I and j components because it's a little easier. We add the vectors together, so 3 plus minus 7 is minus 4, and 4 plus minus 3 is plus 1. Just add the like components. Subtracting, that's 3 minus 7, that's how I got the 10, and 4 minus 3 is how that's 7. So A plus B and A minus B are really nice. Okay, we can get the magnitude of A just by taking the square root of the sum of the squares. And I picked these numbers because it's nice. It's a 3, 4, 5 triangle. So it's the square root of 3 squared, right, the x component. 4 squared gives us 5. And once again, it's the y component of the x component gives us the angle with respect to the x-axis. 4 over 3 is the tangent. Inverse tangent gets us the angle. Okay. How about A dot B? Well, A dot B, remember, gives us a scalar number. Notice there are no i's and j's left, it's just a number. So we take the I components and we multiply them, and we add the product of the j components. So in this case it's 3 times minus 7, product of the I components, plus 4 times minus 3, and that's the dot product. Really nice. Now, I know that there is a relationship between the dot product that I calculate this way. Well, the dot product I calculate this way is just that nice expression. I can also write the dot product as the magnitude of A times the magnitude of B times the angle, the cosine of the angle between them. So I can solve for the cosine. It's just A dot B over the magnitude of A and the magnitude of B. So I just sort of plug in. I have to go back and calculate this B, right? It's the square root of the sum of the squares. And that'll give me, finally, the cosine of the angle between them is this expression which you could calculate. Okay, and the last thing is the cross product. And again, because it's only i's and j's, it's a little easier. So we set up, again, across the top, I, j, k always. And then the first vector A, 3, 4, 0. The second vector, minus 7, minus 3, 0. So once again, we start with the I, 4 times 0, right, minus 0 times 3, that's the first one. Then we go to the j component, Notice that minus sign there, minus j times 3 times 0 minus 0 times minus 7. And then finally, the k component. This is the only one that isn't 0. 3 times 3 minus 4 times minus 7. And notice that this is a vector. It's got components, which we remember are there. Okay.